Okay, we are going to finish up the notes for section 5.6. This section deals with indeterminate forms and L'Hopital's rule. We discussed the first half of this in the video notes for 5.6.1 is what I called it. So this will be video notes 5.6.2. First, we're going to start off with the discussion about what we call indeterminate products. The first paragraph begins by saying, assume that if we let the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equal infinity. So if both of these things are true at the same time, or negative infinity for this g of x limit, then the fact is it wouldn't be clear what the limit of the product of these two things would be. We would be just looking at what we call an indeterminate form of type 0 times infinity, because the limit of f is 0 and the limit of g is infinity. And it's not described here in a particularly convincing or elegant way, I'll admit, but it isn't a bad way to think about it. And what we're talking about here is that you're told that anything times infinity gets infinitely large, and so the answer would be infinity. But we're also told throughout all of schooling that 0 times anything is 0. So the question here is which one of them wins, right? There's a struggle between f and g. If f wins, as it says, then the answer will be 0. And if g wins, then the answer would be infinity, or negative infinity if g was approaching negative infinity. So there's not a particularly convincing answer when you have this struggle, if you would. And the truth may be that sometimes there might be a compromise where the answer is not 0 or infinity, but some finite non-zero number. So we call this the indeterminate form of type 0 times infinity. And we deal with it with a pretty simple algebraic strategy. We take either one of the functions, either the g or the f, and we rewrite them in a quotient, right? Notice that this is in fact true, that f times g is equal to f over 1 over g. If you were to perform the algebra, you'd get right back to f times g. Or you could do it the other way, f times g is equal to g over 1 over f. All right, and if you did the algebra here, you'd get back to that. So both of these cases are good. And the reason why this is a helpful strategy is because it then allows us to convert it to a quotient, which gives us the 0 over 0 or infinity over infinity form that then lets us apply L'Hopital's rule. Again, L'Hopital's rule is what we discussed in the notes for 5.6.1. All right, so it's a pretty simple strategy for dealing with this. Let's roll into the example and see how it works. So in this first example, it's set example 4, we're going to take the limit as x approaches infinity of e to the negative x square root x. First, recognize that if we do some sort of direct substitution here, 1 over e to the negative x, you can think about that algebraically, or you can look at it in a graph. E to the negative x would look like this. This would be y equals e to the negative x. And as x approaches infinity, this approaches 0, right? The curve approaches 0. So we are looking at a 0 times the square root of infinity is still infinity. So a 0 times infinity case is what we're dealing with, all right? So if we take, and this is kind of where a question comes in. It's your choice, it's player choice. Sometimes it's easier to do it one way over the other for sure, and I think that's the case in this problem. When I say easier to do it one way or the other, I mean, do we put the g in the bottom into a fraction, and in this case g is the square root x, or do we put the f into the bottom into a fraction, like the second case shows here? I'm going to write it with the e to the negative x in the denominator. So I'm going to move what is essentially my f down. So if I take the limit as x approaches infinity and I write this square root x over 1 over e to the negative x, then that algebraically is the same as the limit as x approaches infinity of square root x over just e to the x, right? Because the the negative x in the denominator here can be pulled up and made positive in this bottom fraction here, and I can just write it as e to the x. And so now direct substitution would give me square root of infinity is infinity on top, and then in the denominator e to the x, e to the infinity power is infinitely large, so that's infinity. And so now we've got infinity over infinity. L'Hopital's rule can be applied. All right? So if I roll straight into L'Hopital's rule, it says take the derivative of the top and divide it by the derivative of the bottom, and then evaluate the limit. So since the top is technically square root of x, or x to the 1/2 power, then the derivative is 1/2 x to the negative 1/2 power. And of course, the derivative of e to the x is e to the x. All right? So a little algebra to simplify this. The limit as x approaches infinity of 1 over 2 square root x e to the x. Now direct substitution leaves the 1 on top and yields, again, we're putting infinity in there, 2 times square root of infinity is still infinity, and e to the infinity is still infinity. So 2 times infinity is infinity, and 1 over infinity is 0. And so in this case, if we talk about it in terms of a battle here between infinity and 0, the 0 wins. I'm going to be honest with you. In most cases, the 0 wins, but not always. So when in doubt, if it was a multiple choice question or something, you would go with 0 wins. All right. Number 6. So we begin this problem again by analyzing what happens as x approaches 0. In this case, it is a one-sided limit from the right, but that's okay. So if I let x approach 0, then this is 0. I'm definitely going to get 0 times something. Well, what is the something? Well, remember, ln of x graphs like this. Sketch it real quick. ln of x looks like this. There is an asymptote over here as x approaches 0. As x approaches 0 from the right side, positive means from the right. I may have said left earlier. I meant from the right. As x approaches 0 from the right, this function approaches negative infinity. Right? Again, this is y equals ln of x. So we've got a 0 times negative infinity scenario. It is exactly the situation we are describing. It is an indeterminate product, right? So the question is, do we rewrite this so that we have the g function in the bottom or the f function in the bottom? Either way is fine. I'm going to say that just for rule of thumb, logarithmic functions we generally want to leave in a numerator. So we're going to leave the ln up top. We're going to put the x in the bottom. So the limit as x approaches 0 from the right of ln of x over 1 over x, right? Or you could write it as x to the negative 1 if you prefer. So if I differentiate this, if I do direct substitution now, ln of 0, you can't do ln of 0, but the natural log of 0 as x approaches 0 from the right, Notice in both cases, we're not doing direct substitution in here. In both cases, I didn't do it up here either. I actually analyzed it on a graph, right? As x approaches 0 from the right, we get negative infinity on the top. As x approaches 0 from the right, now we have a new function to talk about. This function, 1 over x, when graphed, is our rational function that looks like this, right? And so as x approaches 0 from the right, we get infinity. So this problem, if you do direct substitution, does give negative infinity over infinity. And infinity is not a number, so we can't just cross those off and call it negative 1. That is not allowed, right? So again, using a graph to evaluate the limit as x approaches 0 from the right of ln and the limit as x approaches 0 from the right of 1 over x. These are two very common graphs. It shouldn't be too difficult. We can see that we get negative infinity over infinity. So we do have a L'Hopital's rule scenario. This is one of those indeterminate forms where L'Hopital's rule applies. So let us evaluate with L'Hopital's rule. If I take the limit as x approaches 0 from the right of the derivative of ln of x, which is 1 over x, divided by the derivative of technically x to the negative 1 power from the denominator there is negative x to the negative 2 power. So a little algebra to simplify this, and I get the limit as x approaches 0 from the right of, again, it's 1 over x over negative 1 over x squared, which if I keep the top fraction and flip the bottom fraction and multiply, or in other words, I multiply by the reciprocal of the denominator, I'm going to get really just the limit as x approaches 0 of negative x. All right, and direct substitution here just leaves me with 0. So again, 0 wins the battle. All right, so I do want to point out that in both of these problems, 5 and, number 4 here, and example 4 here, and example 6 here, if you have a calculator on hand and you can graph that function, you can get this answer a lot quicker, right? You graph the function, you analyze what's happening as x, in this first one, as x gets infinitely large, you're going to see that this function actually approaches the x-axis, and the answer would be 0. If you graph this function and you analyze what's happening as x approaches 0 from the right side, you're going to see that it's approaching the x-axis. It's approaching a value of 0. All right? Both cases can be verified on a graph. I'm not going to show that. It's impossible for me to do that on this tablet, but just want to point it out. All right, let's move on. The next indeterminate form we're going to discuss is what we call an indeterminate difference. And to be honest, this topic, this indeterminate difference, normally occurs in scenarios where we have polynomial functions. But it could also occur in random other algebraic functions, like you can see here in example 7, which we're about to get to. All right, this is a purely, we would just classify it as algebraic. So let's go through this paragraph first. Basically, it says if we are taking the limit as x approaches a of f of x, and we get infinity, all right, we're approaching a single value. We're letting x approach a single value, but we get infinity, which means usually a vertical asymptote on that function. And we get infinity for the second one, right, a vertical asymptote. Then the limit of the difference would be infinity minus infinity. Right? We'd be dealing with a situation where we are subtracting. If both pieces approach infinity, right, it's infinity minus infinity. And that is indeterminate. We don't know which one of them is bigger, which one of them wins. If the first infinity is bigger than the second, then we're going to get a positive infinity. If the second infinity is bigger than the first, then we're going to get a negative infinity. So we're not sure. And this indeterminate difference, this battle, has to be solved using a different strategy. Usually, to be honest with you, you'll see it here in the bottom, or in the explanation of this paragraph, it says to find out which one wins, we try to convert the difference into a quotient. All right, by using either a common denominator or rationalize. We might try to multiply by a conjugate and rationalize, or we might factor. There are several different strategies, but it's generally an algebraic strategy. Algebraic. In order to manipulate in some way, manipulate the functions we're given, and create a scenario where you could then apply L'Hopital's rule. So all of this keeps coming back to what can you do to the function, what can you do to the scenario, the given expression, in order to be able to use L'Hopital's rule. So try to get it into a form where we can use L'Hopital's rule, a form that gives you infinity or 0 over 0. So this first example, we are given the limit as x approaches 1 of 1 over ln of x minus 1 over x minus 1. If I let x approach 0 from the right side, this is going to be a little graphing exercise again. If I let x approach 0 from the right side, notice I'm going to highlight here, in let's say this green highlighted one, that is the ln of x function. Remember, ln of x does this sort of thing, right? And as x approaches 1 from the right, we're talking about really this value. We're getting a number close to 0. As x approaches 1 from the right, Struggling with this one, to be honest with you. I'm sorry, that's why. It's 1 over ln of x. 1 over ln of x, not 1 over x. All right, so ln of x, you know what? A graph would be really helpful right here, to be honest with you. And I don't have that. I'm just going to have to say I don't have a calculator. I don't have a way to describe it. But as x approaches 1 from the right in this 1 over ln of x, all right, this is going to approach, this whole limit is going to approach infinity as x approaches 1 from the right. So we are dealing with an infinity in the first piece minus, the second piece is a lot easier to discuss, to be honest with you. I'm just asking you to take it upon faith that what I'm saying here about the 1 over ln of x is true, that as x approaches 1 from the right, it does approach infinity. But I don't have a way of proving that to you because I don't have the graph in front of me. Sorry about that. Sorry. The second one, though, is a little easier to discuss. This red piece, as x approaches 1 from the right, 1 over x minus 1. 1 over x minus 1 is just the rational function 1 over x shifted 1 unit to the right. And so it's going to look like this. This is y equals 1 over x minus 1. And of course, as x approaches 1, this is the x value of 1 here. As x approaches 1 from the right side, we've got positive infinity going on, right? So we do have infinity minus infinity. It's just I haven't proven that green one to you. I'm just asking you to take it upon faith. Sorry about that. All right, so let's let's move on. So we've got an infinity over infinity. What we're going to do here is we're going to manipulate. We're going to play around with this. I'm going to multiply and by a common denominator to try to put this together. So I take the limit as x approaches 1 from the right. This first fraction here needs to be multiplied by x minus 1 over x minus 1. Second fraction needs to be multiplied by ln of x over ln of x. So that would leave me with x minus 1 minus ln of x over the denominator ln of x times x minus 1. All right? And now, if I were to let x approach 1, note, if x is approaching 1, I can just use direct substitution. If x approaches 1, I get 1 minus 1 minus ln of 1. Well, ln of 1 is 0, right? So I have 0 on the top. All right, direct substitution gives me 0 on the top. And in the bottom, of course, 1 minus 1 is 0, times ln of 1 is 0, and 0 times 0 is 0 on the bottom. Now that I have this indeterminate form, I can apply L'Hopital's rule. All right, I got my orange check mark here indicating that it's allowed, it works. So L'Hopital's rule now says to take the derivative of the top and the derivative of the bottom. Not particularly an easy problem, but here we go. The derivative of x, of course, is 1. Derivative of the negative 1 is 0, so I've got 1 minus, and the derivative of my ln of x here is 1 over x. 1 minus 1 over x. Over, in the denominator, I have to use the product rule, all right? Why? Because I have a product. I have ln of x times x minus 1. So the product rule would give me, I might need a little more space to write all this. The product rule will give me first function times derivative of the second. First function is ln of x. Derivative of x minus 1 is just 1, so I don't really need to show that. Plus the second function, x minus 1, times the derivative of the first. Derivative of ln of x is 1 over x. All right? You know, you can use any algebraic strategy you want from this point to kind of simplify and work this thing out, but I think, honestly, the simplest way to play around with this is to multiply both the top and the bottom by x. That's going to help simplify this a little bit. So keep manipulating it algebraically, and I'll get x minus 1 on the top, and in the bottom, I get ln of x, sorry, I should say x ln of x times ln of x plus x minus 1. All right? this 1 over x and this x will cancel, but I still have to multiply the ln of x times x. So that's where this came in. All right, ln of x times x gives me this, and then this expression here times x leaves me with just x minus 1. All right, so it's getting a little cleaner. Now if I try direct substitution, I'm putting 1 in for this x. I still have 0 on the top. And if I put 1 in for the x here, I've got 1 times ln of 1 is 0. And then 1 minus 1 is 0. So 0 again on the bottom. And it feels like we have done nothing. We've got nowhere. But I still have an indeterminate form that allows L'Hopital's rule. I don't know why that... There we go. This is an indeterminate form that still allows L'Hopital's rule. So I'm going to use L'Hopital's rule again. Take the limit as x approaches 1 from the right. Derivative of the top is now much easier. It's just 1. The derivative of the bottom, we're going to have to be careful again. Notice we're repeating now. Repeating a similar derivative. So I have to differentiate this first, which is a product rule problem, right? That gives me the first function times the derivative of the second plus the second function times the derivative of the first. The derivative of x is 1. And then plus the derivative of x, which is 1, minus the derivative of this negative 1, which is 0. So now I am, now I am plus 1 here. All right. So if I clean that just a hair, let's go. We're still working this. This is a pretty complicated question, clearly. It's 1 over, notice I get x times 1 over x is 1, but I have another 1 over here, so that is 2 plus ln of x. Whew. There we go. Simplifies down to just 2 plus ln of x. Now we're getting somewhere, because direct substitution here, the top is 1, and the bottom, when you put 1 into this ln of x, you're going to get 1. I'm sorry, 0. ln of 1 is 0. So our answer is 1/2. 1/2. Indeterminate products that started out as infinity over infinity simplifies to 1/2. Now again, I can't stress enough, if this was way outside the box and you still had a calculator on hand, and I kind of skipped over this 1 over ln of x explanation without a calculator, my best advice is to kind of think about this on a calculator to solve it. But 1 over the limit as x approaches 1 of 1 over ln of x is not, it's doesn't exist. It's an infinity value, which means the limit doesn't exist clearly. But the positive infinity is the important part. The only way to really see that is by plugging in values, and dividing. I guess we could technically kind of talk about that. It's either plugging in values or doing it on a calculator, plugging in the graph. Anyway, going back to the original, if you were to put this whole function, 1 over ln of x minus 1 over x minus 1, into a calculator and graph, and then analyze what happens as x approaches 1 from the right side, you would see that it approaches 1/2. You'd see it on the graph. All right? Let's move on. Example 8. Compute. This one's trig, and I threw a trig one on here just so that we could get a little practice in what happens with different scenarios. So in this case, secant, which is not a graph that students tend to remember in high school very easily, but it's built off of cosine, right? If cosine's doing this sort of thing, secant is built off of it with these asymptotes, right? That's what the secant graph looks like, with these asymptotes throughout the whole thing. That's a really, really crude and ugly secant graph. But as x approaches pi over 2, that's where this first asymptote is. right here. So as x approaches pi over 2 from the left side, secant, we're talking about this branch right here. Secant approaches infinity. All right, so we are looking at infinity there. And then tangent graph is a little easier for students to memorize. Generally, students don't forget that. But tangent looks like this, with an asymptote at negative pi over 2 and positive pi over 2. And as x approaches pi over 2 from the right, from the left. As x approaches pi over 2 from the left, we still have another infinity. So it's minus infinity. We do have an infinity minus infinity. This is definitely a indeterminate difference going on. All right, so we take a little bit of a algebra approach to this, or you could say a trig identity approach, and we start rewriting our function. Secant is 1 over cosine, and tangent is sine over cosine. All right, so if I piece that together, I'm really looking at 1 minus sine over cosine. And now, as x approaches pi over 2, right, doesn't matter that it's one-sided. If I do direct substitution here, sine of pi over 2, all right, let's look at a unit circle if you have maybe forgotten. Sine of pi over 2 pi over 2 is, the angle up here. And sine of pi over 2 is, of course, 1. And cosine of pi over 2 is, of course, 0. The coordinates up here are 0, 1. So we are looking at, for direct substitution, 1 minus 1 is 0 on the top and 0 in the bottom. And now we have it in a form where L'Hopital's rule can be applied. So we're going to use it. I'll put my little h there to say this is where L'Hopital's rule is being used. The limit as x approaches pi over 2 from the right. The derivative at the top is a derivative of sine with a negative in front of it, so I get negative cosine on top. The derivative of cosine is negative sine on the bottom, so I got negative sine. And of course, that simplifies to simply cotangent. The limit as x approaches pi over 2 from the right of cotan x. And cotangent, I don't like that color. Let me try a different one. Let's go with purple. Cotangent is a graph. Notice we're relying on a lot of information that we learned back in pre-cal. Cotangent is a graph that looks like this, with an asymptote at pi. All right, but oops, probably should try that curve again. Looks like this. And at pi over 2 here, at 1/2 pi, at pi over 2, which is right here in the middle, cotangent is approaching 0. So the final answer would be, with direct substitution, cotangent of pi over 2 is 0. And there we have it. Again, I did a lot of remember here, remember this, remember this, remember this. Remember, the graph of secant looks like this, and so we could figure out that secant was approaching infinity if x approaches pi over 2 from the right. Remember, the graph of tangent looks like this, and so tangent approaches infinity if x approaches pi over 2 from the left. I keep saying right, I meant to say left. Then remember that secant is 1 over cosine, that tangent is sine over cosine. Right, a lot of going on here. Remember that cosine over sine is cotan. And then remember that cotangent of pi over 2 is in fact 0. Of course, we could have done this part on the unit circle also. All right, so answer is 0 there. A lot going on. Let's move on. Our last type of indeterminate forms is what we call indeterminate powers. All right, let me write that up here. Indeterminate powers. And to work indeterminate powers, I've got one example here that we're going to use, that we're going just walk through together that is already worked out and just discussed, and then we'll practice one on our own. All right. Indeterminate powers are indeterminate forms where you have 1 to the infinity, 0 to the infinity, or 0 to the 0 power. And these are a little harder for students to remember because the truth is you want to rely on some of that information that you kind of assume to be true your whole career in mathematics. When you started talking about 1 raised to any power, you said 1 raised to any power is 1, so it doesn't matter if it's infinity. Or the second one is a little less obvious, infinity to the 0 power. You did say that anything raised to the 0 power is always 1, so why isn't the second one supposed to just be 1? Well, because infinity is not a number. And then 0 to the 0, well, anything raised to the 0 power is 1, but then also 0 raised to anything is supposed to be 0. So clearly that's a confusing conundrum there. So these are our 3, all right? And we do get those when we take some limits sometimes, and this first example shows us one. So these arise from functions that have variable bases and variable exponents. And we encountered this one already, all right? When we had this sort of situation in the past where we had a function, we said a function raised to a function of x, and we wanted to take the derivative of that. We had a rule before where we said if this is something you are asked to do, take the derivative of a function raised to a function, use logarithmic differentiation, all right? Well, we're going to do something similar to that on these limits. We're going to use logarithms to solve them. So let's walk through this example. All right? It says the limit as x approaches infinity of 1 plus 1 over x to the x power. All right? We begin by substituting directly in for x, and 1 over infinity is 0, so this term goes away. We're left with 1 to the infinity power. So direct substitution does give us, all right, direct substitution here does give us 1 to the infinity, which is our indeterminate form. So we know we have to do some more. So what we do is we assume that this limit exists and is some value. All right, assume the limit exists. And then we'll say, okay, if it exists, let's set it equal to y. You can call it anything you want, but y is the easiest. All right, so here they've set it equal to y. All right, right here. Then take the natural log of each side. All right, if we take the log of each side, you see that here. The rules for logarithms tell us that if a function is continuous, rules for limits, tell us that if a function is continuous, we can move the limit notation throughout. So I can actually pull this limit, this ln, this log, inside and put the limit on the outside, and that's what's happened here. So the ln was moved. As long as the function is continuous, which natural log is, this is possible. All right, we can kind of move in and out. So now, if we let x approach infinity, we have infinity from this piece times what we already said that this, well, we haven't said this one, I'm sorry. If we let x approach infinity here, this is 0, and we have natural log of 1, which is 0. So we have infinity times 0. We're left with this form, infinity times 0. So how do we solve that? We discussed this in the beginning of this video. We solve it by rewriting one of these as a quotient. So we're going to put remember I said, generally speaking, we leave natural logs in a numerator. So I'm going to put this x in a denominator as 1 over x. All right? And if I do that, notice the numerator is the same. They've written it a little bit more condensed, but it is still the same as this natural log of 1 plus 1 over x. And the denominator is 1 over x. Now if x approaches infinity, this is 0, and this is 0. 1 over infinity is 0. So the top is 0, the bottom is 0. We now have this indeterminate form that we keep looking for that allow us to apply L'Hopital's rule. Right? So with L'Hopital's rule, we start taking a derivative. That's what they're doing here. L'Hopital's rule is now being applied. All right? So the derivative at the top is 1 over the input. It's natural log, so 1 over the input and then this is the derivative of the input. So 1 over 1 plus x squared, that's here. Sorry, 1 over 1 plus 1 over x, that's what I meant to say, is here. And then the derivative of the 1 plus 1 over x is just negative 1 over x squared. They've condensed it, they've kind of cut a few steps out, but trust me when I say that this numerator is a derivative of that numerator. And then the derivative of 1 over x is negative 1 over x squared. All right? Again, in the denominator. So a little bit of algebra, or you could say a lot of algebra from here to here, but they're just simplifying. To get from this step to this step, they just simplify, just using some algebra. I'm not going to show all that for the sake of time in this video. All right, so with all of that, we get down to the limit as x approaches infinity of 1 in the numerator over this. Actually, the simplifying is not all that bad. If you notice, this would cancel this out, and then you're just left with that. So not too terrible. The negative 1 over x squared divided by negative 1 over x squared, those will cancel. So if x approaches infinity, we've got 1 in the numerator, we've got 1 plus 0, so you got 1 over 1, we get 1. Now, that is not our answer, because what we said was the natural log of y is equal to 1, right? That's what we did at the beginning. We took the natural log. So the limit of the natural log equaled 1. And so now, if we solve this, or you could say exponentiate, e to the ln of y is y on the left side, and e to the 1 is e. So the limit y is equal to e. And this is not new. We actually have already discussed this. We discussed this when using applications for exponential functions back in the compound interest and continuous compound interest section. All right, so this is something we had already confirmed in a previous problem. Okay, great, beautiful little eloquent problem here, already worked out in full. Hopefully it made sense as I walk through. Let's discuss a little bit with indeterminate powers, practice one problem, and then I'll wrap this up. It's already a long video notes. All right, so a summary here of these indeterminate powers. This is a summary. The three types in particular, again, we're talking about situations where we have the limit of a function raised to a function. We have type 0 to the 0, type infinity to the 0, and type 1 to the infinity. All right? In each of these three cases, the easiest strategy, the strategy I recommend, is that you assume that the limit exists and then take the natural log. So assume it exists, call it y, and then take the natural log of both sides, evaluate the limit in that form. All right? You could also do it this way by rewriting it with base e, but I'll tell you that that's a tougher strategy, and most people would not do that. All right? Recall that both of these methods were used when we were differentiating e to the x and a to the x and ln of x and so on. We used both of these strategies before. All right? So here we go. Let's practice. Number 6. This is actually a fairly long problem, unfortunately, but I'll try to make it as quick as we can. Here we go. Start out. If x approaches 0 from the right, well, actually, let's not even go into those details. Sine of 0 is 0, and x approaches 0 from the right. We've got a function raised to a function. We've got 0 to the 0 power here, right? This is definitely a 0 raised to the 0 power. But the dead giveaway is that we have a function of x raised to a function of x. And when you have those two things, you're going to end up saying, all right, this limit equals y. All right, y is equal to this whole limit. And then I'm going to evaluate the natural log. So we take the natural log of both sides. All right, if I do that, then it allows me to pull this x in front. So first off, I'm going to say I can move that limit notation to the outside on the right and put the ln on the inside. And then I can pull this x out in front of the natural log using the power rule for logarithms. So I've got x times ln of sine x. All right. Now, if x approaches 0, right, if x approaches 0, I have 0 times the natural log of, and notice we're letting it approach 0 from the right. So natural log of a sine of 0 is 0, but if it's from the right, it's a really, really, really small number, close to 0, which is technically negative infinity, right? Again, the natural log function graphs like this. And so sine x approaches 0. Sine of x approaches 0 as x approaches 0. And so ln of sine x it's like saying ln of sine x is approaching 0, or ln is approaching 0 from the right, which means negative infinity. All right, so all of this is equal to 0 times infinity. All right, all of that just basically say I've got a 0 times infinity case. And so we started with a 0 to the 0 case. We've transformed this to a 0 times infinity case, and we handled the 0 times infinity case by rewriting one of them as a fraction in a quotient, right? So I'm going to put the x in a denominator here. I'm going to rewrite this now and say, let's call it a limit as x approaches 0 from the right of ln sine x over 1 over x. All right, and now if x approaches 0 from the right, the top function is still approaching infinity, but the bottom function will also approach infinity. Remember, 1 over x is that reciprocal function as x approaches, let me say this. This is y equals ln of x. Oops. Would have helped if I labeled this graph to begin with. So that's y equals ln of x, and 1 over x. See, I'm relying on a lot of what is supposed to be prerequisite knowledge here. This is y equals 1 over x. 1 over x, as x approaches 0 from the right, also approaches infinity here. All right? So this is now an infinity over infinity. Actually, a negative infinity over positive infinity problem. Negative infinity over positive infinity. Now that it's an infinity over infinity, I'm going to stick with this orange check mark thing. I can use L'Hopital's rule. Okay, so let's go at it. If I apply L'Hopital's rule here, I'm going to switch colors. I'm just using it on this limit here. L'Hopital's rule says the limit as x approaches 0 from the right of 1 over the input, 1 over sine, times the derivative of that input, derivative of the sine is cosine, over, the derivative of 1 over x is negative 1 over x squared. It's about the third time we've done it now in these notes. So that, if I want to clean this up a little bit, turns into the limit as x approaches 0 from the right of, really, if you can stick with me here, this becomes cosine over sine in the top, and then, right, cosine over sine in the top, and then negative 1 over x squared in the bottom. Well, the truth is, if I move both of these, if I take the top and I flip it and move it down, and I take the bottom and I flip it and move it up, then I'm really going to be left with negative x squared in the top over tangent in the bottom. All right, play around with that if it doesn't quite ring a bell with you, but just because I'm running out of space and time, I want to say that this is true. All right, this simplifies into this. Then I'm looking at the limit as x approaches infinity from the right of negative x squared over tan. Just going to rewrite it here. If I do direct substitution on this, I get 0 over 0. Still an indeterminate form. If you're working this problem on your own, you're going, holy crud, when is this thing going to start to work out? I feel like I've done all this work and I'm not getting anywhere. But the fact is you are. It's getting more and more simple as you go. We're almost there. If I apply L'Hopital's rule again, the derivative of the top is negative 2x, and the derivative of the tangent is secant squared. And here, as x approaches 0 from the right, direct substitution gives us 0 on the top, and secant of 0 is 1, which means this limit equals 0. And so what we're saying is that, remember, if you go all the way back to here, what we're saying is that ln of y, all right, therefore, ln of y must equal 0, which means y is equal to e to the 0, or 1. The answer to our limit is 1. Whew, what a problem. That was a monster, huh? If you were to graph this from the start, sine of x to the x power, and analyze and try to see what's happening as x approaches 0 from the right side, you would look at a graph and you would see that it approaches a value of 1 from the beginning. A lot of calculus goes into proving why that's true when you could have just looked at it on a graph to begin with. Notice we had to rely on knowledge of previously learned graphs in order to even do this problem. Okay. Quick summary here of the rest of it at the end, and then I'm done. I'm not going to talk about the mean value theorem, Cauchy's mean value theorem. It's not important. So don't worry about the tail end of these notes if you're looking at the key on the portal. Again, the forms, all the forms that we've discussed so far, 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0, 0 to the 0, 1 to the infinity, and infinity to the 0. These are our 5, 6, 7 forms. How many are there? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 forms. These are the indeterminate forms that we will play with. There are other forms that are determinate, that are definitive, and they're listed here. These are determinate forms. Meaning their answers are true. They are set in stone. Infinity plus infinity, that one's pretty obvious. Negative infinity minus infinity, that one's pretty obvious. That will approach negative infinity. The other two here are not so obvious, and I am not going to prove them. All right, it would take way too long. But infinity to the 0 to the infinity is 0 always. Notice that's different than what we had here. 0 to the 0, and infinity to the 0. Those were indeterminate. But here, 0 to the infinity power is going to approach 0 every time. And then in this case, 0 to the negative infinity power will approach infinity every time. All right, you can memorize those, but it's going to show up so infrequently, and it's not a big deal. And then this last little bit here, everything here at the tail end, is just reminding us, please, please, please make sure, if you read through this, please make sure that you verify that L'Hopital's rule can be used before you try to use it. And what I mean by that, please verify that you get infinity or 0 over 0 or infinity over infinity before applying L'Hopital's rule. We've discussed that. We've discussed it in the previous notes. It's now been discussed multiple times. That is such a key factor. And you can see another example here why if a student was to apply L'Hopital's rule without verifying, they would get the answer wrong. All right, the part I just highlighted there. All right, I'm going to end because these notes are very long already. Hopefully this was helpful. We can discuss in class if there are questions.